Hello everyone, welcome back to my YouTube channel. Myself Nishchita SN, 3rd SEM BE, Department of Electronics and Communication Engineering in Sri Venkateshwara College of Engineering, Bangalore. In this video, I am going to discuss about the subject network analysis. The topic is about one theorem, that is the Thevenin's theorem. First, we know about the introduction of Thevenin's theorem. Thevenin's theorem is a powerful technique used in electrical circuit analysis. It simplifies complex circuits into an equivalent circuit containing just a voltage source and a resistor. This theorem helps in analyzing and solving circuit more efficiently. The statement of the Thevenin's theorem: in any linear bilateral network with output terminal A and B shown in figure A can be converted into a single voltage source VTH in series with an impedance ZTH as shown in the figure B. The voltage source is called Thevenin's equivalent voltage source and is equal to open circuit voltage measured across the load terminal A and B. The ZTH is called the Thevenin's impedance and is equal to total impedance of the network measured from the load terminals by making all the sources in the network zero. The proof of the Thevenin's theorem: consider the network as shown in the figure. Using the current division rule or branch current formula, load current IL equals to R2 divided by R2 plus R3 plus RL. RL means load resistance and 3 resistor R2 and R3 into I. To find the I value, so rewrite the circuit like this. R2 is parallel with R3 plus RL. Next we get R2 into R3 plus RL divided by R2 plus R3 plus RL. Multiply R2 in both RL plus RL. Next we get R2 into R3 plus R2 into RL divided by R2 plus R3 plus RL. From the above network we know that I is equal to V divided by R. So I equals to V divided by R1 plus this value, that is R2 into R3 plus R2 into RL divided by R2 plus R3 plus RL. Next multiply this R2, R3, RL with R1. So we get I equals to V divided by R1 into R2 plus R1 into R3 plus R1 into RL plus R2 into R3 plus R2 into RL divided by R2 plus R3 plus RL. Substitute this I value into equation number 1. We get IL equals to R2 into V divided by R1 into R2 plus R1 into R3 plus R1 into RL plus R2 into R3 plus R2 into RL. This is the Thevenin's theorem equation. Next, we verify this equation. First step, to find VTH, remove the load resistance, that is RL, and find open circuit voltage across A and B. We know that according to Ohm's law, V is equal to higher. So VTH is equal to I into R2. VTH is equal to I is equal to V divided by R. So V divided by R1 plus R2 into R2. This is the VTH value. Next we find the RTH. Make all the sources, that is a load current and the load resistance and the voltage, make it into zero and measure the total resistance of the network looking in the terminal A and B. RTH is equal to, that is Thevenin's resistance, is equal to R3 plus R1 into R2 divided by R1 plus R2. Make R1 and R2 resistance with parallel. So RTH is equal to multiply with R1 plus R2 into R3. We get RTH value R1 into R3 plus R3 into R2 plus R1 into R2 divided by R1 plus R2. Last step, write the equivalent circuit load across the AB. Lastly, find the load current. IL equals to VTH divided by RTH plus RL. Already we find the VTH value and RTH value. Substitute that one. And finally we get IL equals to V into R2 divided by R1 into R3 plus R2 into R3 plus R1 into R3 plus R1 into RL plus R2 into RL. This is the verification of the Thevenin's theorem. Based on this Thevenin's theorem, we solved one problem. Problem is like this. Using Thevenin's theorem, find the current flowing through R1 resistor for any network as shown in the figure. First, we find the VTH, that is Thevenin's voltage. Open the circuit voltage, have 6 ohm resistor. Is load, have it remove. Means 6 ohm resistor, that is the load resistance that can be removed. Remove it. Remove R ohm resistor and find the open circuit voltage across A and B. In this figure, we apply the load analysis method. We apply the load analysis method in loop 1. We get 4i1 plus 4i1 equals to minus 20 plus 4. 4 plus 4 is 8i1 equals to minus 20 plus 4 is minus 16. I1 equals to 16 divided by 8 is minus 2. We know that VTH is equal to VA minus VB. VB is 0. So VA equals to VTH. VA equals to 4i1 plus 20 minus 5. 4 into I1 value we already find minus 2. So minus 8 plus 20 minus 5 is equal to 7 volt. VA equals to VTH is equal to 7 volts. Next step, to find the RTH, make all the sources in the network 0. Make R1 is parallel with R2. So we know that parallel formula R1 into R2 divided by R1 plus R2. So Thevenin's resistor RTH is equal to 4 into 4 divided by 4 plus 4 plus 2. So 4 into 4 is 16 divided by 4 plus 4 is 8. 16 divided by 8 is 2 plus 2 is 4 ohm resistor. RTH value is 4 ohm resistor. Last step, to find the load current. So I equals to VTH divided by RTH plus RL. VTH value is 7. RTH value is 4 plus load current is 6. Load resistance is 6. 7 divided by 10 is I equals to 0.7 ampere. What are the advantages of this theorem is, Thevenin's theorem simplifies complex circuits, making them easier to analyze and solve. It reduces the number of components in a circuit, reducing complexity and calculation efforts. The theorem provides an efficient way to find the voltage and current across any load in a circuit. Limitation of this theorem is, Thevenin's theorem is only applicable to linear bilateral circuits. It assumes that the circuit is at steady state conditions. The theorem may not accurately represent the behavior of circuit with active elements like transistor or operational amplifiers. Conclusion is, Thevenin's theorem is a valuable tool in electrical circuit analysis. It allows complex circuits to be simplified into an equivalent circuit containing a voltage source and a resistor. By applying this theorem, engineers can efficiently analyze circuit and design practical systems. Thank you for watching my video. Please like my video.